thanks a lot, and thanks a lot for organizing the summer school, Philippe. And yeah, and especially thanks for having me so that I can give my first talk at a conference. So what I'm going to talk about are orthogonal discriminants of finite groups. And this is actually the title of my master's thesis, which I finished recently. And this is what I'm going to talk about today. So I'm going to start with a quick overview. And first of all, my thesis was part of a project from my supervisor, Gabriele Nebe, together with Richard Parker and Thomas Breuer. Well, and the goal was to compute these orthogonal discriminants, which I'm going to talk about, for finite simple groups and create a database of them. So these orthogonal discriminants are, so to say, some sort of invariant of a finite simple group that arises naturally in the context of what we call orthogonal representations. And an orthogonal representation is, well, basically speaking, just a regular linear representation together with a quadratic form that is non-degenerate, which is fixed by the group operation. So in order to introduce orthogonal representations, I'm first going to talk about some basics of quadratic forms, and then about some basics of representation theory of finite groups. And afterwards, we can then talk about what is an orthogonal representation and what are these orthogonal discriminants. And as we want to compute orthogonal discriminants and create a database, I'm of course going to talk in the end about on some methods that we use to, well, compute some of these orthogonal discriminants. So let's get started with some basics on quadratic forms. And first of all, I'm going to fix some notation for basically the entire talk. So K is going to be always a field in characteristic 0, always, and V is going to be an n-dimensional vector space over the field K, and it's always going to be finite dimensional. And I guess you're very familiar with this basic definition of a quadratic form. A quadratic form is nothing but a map from the vector space into the base field, together with, well, this theoretic condition that you can pull out squares out of the argument of a quadratic form, but you have to square it. And the second one is that this, this map that's defined by this formula is a symmetric bilinear form on the vector space V, which is also sometimes called the polarization. And, well, in case you're not familiar with quadratic forms, then you can think about them as, well, basically symmetric bilinear forms, because as the characteristic is not 0, they are essentially the same. So the theory of symmetric bilinear forms and quadratic forms is the same. This is due to this following remark. If we have a bilinear form B on the vector space, then you can always define a quadratic form just by saying the quadratic form QB of X is a quadratic form B, and you just put in the same argument. You put the same vector in both arguments. And you can see it easily compute that this is quadratic form, and this polarization will be 2 times B. So if you can divide by 2 in your base field, you get the same again. So, OK. And one nice way to think about quadratic forms, at least for me, and I find that this is very instructive, is to just think of the quadratic form as a Gra matrix, basically. So a symmetric matrix. And you can do that by just choosing some basis E of the vector space and, well, just take the usual Gra matrix from this from this bilinear form BQ. And excuse me. And then the quadratic form I'm sorry, my voice is giving up a little bit. OK, so then the quadratic form is called non-degenerate if the bilinear form is non-degenerate. So if the determinant of this Gra matrix is a unit in the field. And now we come to 2 very important invariants of quadratic forms. And, well, the first one is the determinant of Q. This is just then the determinant of the Gra matrix, but up to squares. We do this because, well, we change bases for Gra matrix this way that you can see here. So we multiply with the transpose from invertible matrix from the left and the matrix T from the right. So we get squares on the determinant. So this is why we defined here, just to make it independent of the choice of the basis. And the discriminant is basically the same square class up to a sign. And in case you're not familiar with quadratic forms, this definition might seem a little bit weird, but it's just because in the theory of quadratic forms, this sometimes behaves better than just a determinant. So this is the definition of the determinant and the discriminant. And during this talk, we will be interested in non-degenerate quadratic forms. And in this case, then the determinant of B will be invertible, and so the determinant and discriminant by definition will be just square classes of units over the base field K. Now we want to collect some properties of this invariance, and the first one is very important. So what happens if you have a non-degenerate quadratic form Q and you take some scalar A, and say you want to consider the form A times Q, so just multiply the form by the scalar. Well, what you can then easily check just by considering Gram matrices is that this new quadratic form A times Q will also be non-degenerate. You just multiply the Gram matrix by a scalar. It's still invertible. And if n is even, then the determinant and the discriminant will stay the same. So if you have an even dimension, these invariants stay the same under scaling the quadratic form. And the second property is, well, what happens if we consider field extensions? So let's say you have a quadratic form Q on your vector space V, and you extend the base field K by some field extension L. Then just by extension of scalars, you get a new vector space V, L, which is just L tensor V. And you, of course, can then just extend your quadratic form to this vector space in the natural way, also just by extending scalars. And then, because the Gram matrix stays the same, you get the discriminant of this new form QL. It's just the discriminant of Q up to squares in L. You just add the squares in L. So I'm going to show two very basic examples. These are like the easiest examples that you can come up with. So we start with the vector space V with the basis E1 up to En. And then you just take the quadratic form Q on V, well, whose Gram matrix will just be the Gram matrix of the standard inner product. Then this is, of course, regular. This is then, of course, non-degenerate. The Gram matrix is just the n by n identity matrix. And, well, so then the determinant is just 1. But keep in mind, we are talking about square classes, so it's the square class of 1, or just the class of squares in the field. And the discriminant will basically be 1 up to a sign. So if n is congruent to 1 or 2 modulo 4, it will be the same. Or if it's 2 or 3 mod 4, then it will be minus the discriminant. And now if you have this first space, you can consider a subspace in this first space, which we call W. And this is just, well, the linear combinations of the standard bases such that the coefficients sum up to 0. And, well, this is an n-1 dimension subspace because you can just write down the spaces. And you can now restrict the quadratic form Q to the space W. And you find that this will have this Gram matrix. Yeah, just apply the standard inner product to these, and you will see this is the Gram matrix. And, well, you can show by induction that this will always have the determinant n. And we are working characteristic 0, so this is invertible. And we also get a non-degenerate form. And for later, we will call this quadratic space an minus 1 over K. OK. That's about it, what I want to tell you about quadratic forms. And I just want to point out the most important things. So the first one is just the reminder of the definition. A quadratic form is nothing but a map on the vector space that induces a bilinear form BQ on the same space. And we call the form Q non-degenerate if and only if BQ is non-degenerate, or equivalently if the determinant of any Gram matrix is invertible. In this case, we have these two invariants, and there are square classes of units in the field. Now, if the dimension is even, these invariants are independent of scaling. This is very important for later, for the definition of the orthogonal discriminant. And finally, if you know the discriminant of Q, then you know it for every field extension Q. Then you know the discriminant of QL for any field extension, which we discussed before. OK, so now we come to the representation theory part. And here we're going to start with just a finite group. And, well, the basic idea of representation theory is that groups are hard to understand, so we want to use linear algebra. So the basic definition of representation theory is the following. Linear K representation of G on the vector space V is nothing but a group homomorphism from the group into the automorphism group of the vector space. Or if you prefer matrices, you can just choose a basis, and then you will get here the full then you get here the matrix ring of the invertible matrices. And the dimension n of this vector space is then also called the degree of the representation. So why do we do this? Well, the advantage is we can now consider eigenvalues of group elements, we can consider determinants, we can even add group elements, and importantly, we can consider traces of group elements just by considering these images in, well, this space here. And yeah. Another way to, well, basically do representation theory was proposed by Emmy Noether in the mid-1920s. And she proposed to just consider the group algebra and, well, modules for this group algebra. And this is equivalent to what we see above here. I'll get to that on the next slide. But just as an example, which we'll use on the next slides as well, just take the group A5. This has 60 elements, the alternating group on 5 elements. And then KG is just a 60-dimensional algebra over the base field. Yeah, because the basis is just the group elements. So as I said before, these two concepts of matrix representations or, well, KG modules are the same. That's why I'm going to just skip between these two concepts, and sometimes we'll talk about KG modules, and then I'm going to talk about representations, but they are the same. So what you can do is, if you start with a representation, x of g on the vector space, then you can always get a KG module structure on this vector space just by saying, okay, I have my group element g, and it should act on the vector v just by applying this automorphism to v. X of g applied to v. Or if you have matrices, you just multiply the matrix x of g to v. Conversely, if you have a KG module v, then, well, the group acts on the vector space because it's a KG module, and it acts as automorphisms of the group because group elements are invertible. So you get a representation again. So these two concepts are actually the same. And now the very nice theorem of Maschke basically tells us that the category of KG modules is semi-simple. So the theorem is the following. If the characteristic of K does not divide the group order, then KG is a direct sum of simple algebras. And remember, in our case, the characteristic of K is 0, so this theorem always applies. Just as a side note, actually the converse of this statement also holds. So on the contrary, KG is a direct sum of simple algebras if and only if the characteristic of K does not divide the group order. So here as an example, you have two compositions of group algebras into its simple components, into its simple algebras. And as you might know, a simple algebra is always isomorphic to a matrix ring over a division algebra over the space field K. And in this case, you have QA5. It decomposes into the simple algebras Q adjoint root 5 to the 3 by 3, and Q to the 4 times 4, and Q to the 5 times 5. And similarly, you get the composition over the complex numbers, with the only difference being that this simple algebra splits further into two direct sums. And, well, you can also note that the group order decomposes similarly to how the group algebra decomposes. Now what we can do is, as I said, such a simple algebra always looks like a matrix ring over a division algebra. And, well, to each such a simple algebra always only has one simple module up to isomorphism, which you can just identify always with the column space. Like for this component Q to the 4 by 4, the simple algebra, the unique simple module would just be the column space Q to the 4 times 1. So what you can then do is you call this module, let's say V, and then if you choose a basis, then you get a matrix representation, just as before. And now we want to consider the traces of these matrices, and this is then called a character. Or, well, you can just call it an irreducible character because it comes from a simple module. And as I said, the definition of a character goes as follows. It's just a class function from the group G into K, and you just take the traces of the matrices in the image. And clearly, chi of 1, by that I mean the identity of the group, is just a dimension of V because, well, the 1 gets mapped to the identity matrix of the corresponding size, and this is just a dimension of V. And, well, again, the easiest example you can think of is just the trivial KG modulo K. So that's the base field, and you act on it just by saying, okay, group element should act on, well, element on the field just by doing nothing, acting as an identity. Then x of g will just be, well, the 1-by-1 matrix with 1, doesn't do anything, and the character will be constant to 1 on every group element. Of course, the character is irreducible because it has degree 1. You can't further decompose it into smaller characters. And we denote this character chi by this, well, specially written 1. And the case we are particularly interested is the case of the C characters. And this is usually denoted by r of g in the literature. And the values can be read off of the so-called character table, which you might have seen for some groups. In case you have not seen one, here's the one for the group A5. So you have 5 irreducible characters, you have 5 conjugacy classes. Remember, characters are class functions, so they are constant on conjugacy classes of the group. So this basically tells you the whole representation theory of the group A5. And the definition we're going to need later is the definition of the character field. So if you take an absolutely irreducible character over the complex numbers, the character field is just the smallest field over the rationals that contains all the character values. And you just adjoin all the character values. And as an example, just look at the table, chi1, chi4, and chi5 have rational character field or trivial character field. There are only integers here, and the character field of chi2 and chi3 will be q adjoint root 5, because you have roots of 5 here. And now one important property and why the character field is interesting for us is the following. If you have any field with an LG module V that realizes this character, so you have a field L and a module there that basically has a prescribed character chi, then you know that the character field is contained in L. Simply because if you think about this in terms of matrices, then you have matrices over L, and the trace of these matrices is the character. And of course, then the sum of the elements of the matrices on a diagonal will also still lie in L. And so L contains all the characters, and in particular it contains the character field, because as I said, the character field is the smallest field that contains all the character values, just by definition. Okay, takeaways. Once again, linear K representations and KG modules are the same concept. This is why I'm just going to switch between them when I need to. And characteristic 0, the group algebra KG is semi-simple. It was Maschke's theorem. And so we only need to study the simple KG modules. Yeah, because it's a semi-simple category. If we understand the simple objects, we understand all the objects. Now, a simple KG module V is uniquely determined by its irreducible character, chi V. And, well, if you have such an irreducible character over the complex numbers, then its character field is the smallest field L, of which an LG module with character chi can exist. That's what I said at the end. And with all of that, we can now come to the object that really interested us, namely orthogonal representations. So the definition at first looks quite a lot, but I'm just going to give the basic idea first. So an orthogonal representation is just a usual linear representation as we've seen before in the representation theory part. But additionally, it has to fix a non-degenerate quadratic form on the vector space. That's the basic idea. So you not only have a KG module structure, but on this KG module, you also have additionally a quadratic form that is non-degenerate, and that is fixed by basically these matrices x of g in the image. More formally, you just take a linear K representation of G, and you define the space Q of X, which is just a vector space of quadratic forms on V. That additionally is G invariant. So this property means just G invariant. X of G acts, well, trivially under this quadratic form, or as an orthogonal map on this quadratic form. And if this space Q of X contains a non-degenerate quadratic form, then we call X an orthogonal representation. So it just has more structure than a regular representation. And if this is the case, we can still consider its character, and then we also can call it orthogonal. Well, of course, because matrices, representations and KG modules are the same, you can state this in terms of KG modules and could talk about orthogonal KG modules. That's quite clear. Now, the important proposition is the following. which basically tells us how we can decide whether a character chi is orthogonal if you take a complex irreducible character. Well, the theorem is the following. If chi is orthogonal if and only if this indicator, which can be computed like this, evaluates to 1. And yeah, this indicator can always take 3 values. And maybe it's a good idea to give a bit more context for this, because I talked a bit about the group algebra. So as you might remember, the group algebra is semi-simple, so it decomposes into a direct algebras. And simple algebras are nothing but division rings, full matrix rings over division algebras. And there are precisely 3 division algebras of the real numbers up to isomorphism. The first one being just the real numbers. How do I do this? Yeah, maybe like this. We have the real numbers. Then we have the Hamilton quaternions, which I'm going to denote by this H. And finally, we have just the complex numbers. Well, this algebra, it's still a division ring, but it's not central simple. But we don't care about that. We have the complex numbers. And here we have the characters chi, the irreducible C characters that have indicator 1. And you get the matrix algebra of size chi1 by chi1 of the real. For the Hamilton quaternions, these are, I'm just going to write chi. These are those with indicator -1. And here you have also chi1 times chi1, but you have to divide out the Schur index, which is 2 in the case of the Hamilton quaternions. And finally, you have to be careful here. You have pairs of complex characters, and these are those with indicator 0. And also you have chi1 by chi1. So let me take maybe another color. The orthogonal characters correspond to these. So they come from these real matrix rings. They come from these simple components. Here you can find the orthogonal characters. In particular, if chi is orthogonal, then you know that, well, the character chi always takes real values. And in fact, if you think a bit about it, the character field Q of chi is totally real. I hope the people on Zoom can still read that. So here you can find the orthogonal characters. These are those with indicator 1. So in particular, these are precisely the characters that come from irreducible real representations. OK. But really, the one thing that I want you to take away from this is that not this formula, but that is very easy to compute. If you have the character table, these are all entries in the character table. Just remember the character table for A5. You can just read off this values here and compute the sum. So it's very easy to decide if you have an orthogonal character or not. And if this is the case, that you have an orthogonal character, then, well, then you know that this set Q of X, this space of G-invariant quadratic forms, is one-dimensional and spanned by a non-degenerate quadratic form. This is just a consequence of Schur's lemma, because the character is real valued, so this vector space V is actually self-dual, and any bilinear form induces an isomorphism between the vector space and its dual. And by Schur's lemma, this must be one-dimensional. So now, I want to define the orthogonal discriminant. And for that, we're just going to collect some previous results. The first one just being the one from the last slide. So if I have an orthogonal representation and an orthogonal character, then the set Q of X is one-dimensional and spanned by a non-degenerate quadratic form Q. And the other thing that I talked about when we discussed quadratic forms is, well, what happens if we rescale a form? Then this invariant, the discriminant, is stays the same, no matter which form you take. So if you now just combine these two propositions, you get, I guess you know what will come, you get the following definition. You just take the both assumptions that we have here. So you're taking an orthogonal character such that the dimension is even. And additionally, you need this technical condition that there is a representation of the character field with this character. And now you can take any quadratic form that's not the zero form in the space Q of X. Then the proposition above tells you the space is one-dimensional and you did not take the zero, so you took a non-degenerate quadratic form. And actually, it doesn't matter which one you take, due to the second proposition, they all will have the same discriminant. And then we just define the square class disc of chi to be the discriminant of Q. And remember, it's the square class over the character field. And this is then called the orthogonal discriminant. So it's just the discriminant of a non-degenerate quadratic form and of a one-dimensional space of non-degenerate quadratic forms. And because the dimension is even, it does not matter which one you take. The scaling is unimportant. And we give it a special name because it lives over the character field, and the character field was the smallest field over which you can hope to realize such a character chi. So I want to comment a bit on this definition, or a bit on the property of an orthogonal discriminant. Here above you just see the definition again. Now the orthogonal discriminant has the following property. If you have an orthogonal character, then the discriminant satisfies the following. If you take any field where you have a representation X that has the character chi, so the character chi is realizable over the field L, then you know that the discriminant of any non-degenerate form Q, which you can find in the space Q of X over this larger field L, then the discriminant of this one, of this form, will just be the orthogonal discriminant up to squares in L. And this immediately follows what I told you about what happens with quadratic forms over field extensions, because the character field is the smallest field over which you could realize a character, over which you could realize a representation with a character. And if you have a representation there, and you just extend the base field, you can read off the discriminant of this. I call this form QL. So you just have to imagine that this form is now QL. And you know its discriminant. It's just the discriminant of the form which lives over the character field, which was the smallest field. And now you just add the squares of L. And in fact, you can use this property as a definition for orthogonal discriminants, and you will get something more general. Actually, you don't need this technical property which I mentioned here, that there must be a Q of chi representation, X with this character chi. Of course, you then have to show that such a square class exists, because that's not obvious. And this is really a condition that I told you here, because what can happen is there might be a non-trivial Schur index involved in some of the decompositions of the group algebra. So it might happen that you have a character chi, which, well, for which you don't find representation over its character field. That can happen, but you can always realize it over. You can always realize the character 2 times chi over the character field. So if you want to use this definition, you can do it. It's more general, and, well, in some sense it's better. But I think it's way easier to motivate the above definition with the character field being involved there. That is some sort of the smallest field for which you can realize the character, and then you get this property in a natural way. OK, takeaways. So an orthogonal K representation is just a linear K representation that additionally leaves a non-degenerate quadratic form invariant. That's just, again, the definition. And here's, again, the definition of an orthogonal character. Chi is orthogonal. Yeah, no, sorry. That's not the definition. If chi is an orthogonal character, then the form Q from above is unique up to scalars. And then if you have the character field and n is even, the orthogonal discriminant is just defined to be the discriminant of Q over the character field if you are in this situation. So now that we know what the orthogonal discriminant is, we can talk about how we can compute that. And this is actually, in general, not that easy, because there's not really a general method on how you can compute orthogonal discriminants, because you have to do this for very different groups and also for very different sorts of representations. So there's not really much hope in finding a general way of doing this. However, there are some techniques that you can hope to use that might apply in for your character that you're currently working on. And some of these are, for example, you can consider group and field automorphisms of G or of the character field. What I mean by that is you just take the automorphism group of G and it acts on the characters. And characters that lie in the same orbit under the operation of G have the same orthogonal discriminant. That's just because if you imagine you have a representation for two characters that are conjugate under some automorphism of G, then the images, well, basically the matrices involved in the images will be the same, because an automorphism just permutes group elements in some way, but doesn't affect the matrices in general. So they fix the same quadratic form. And you can also consider, well, basically the Galois group of the character field over the rationals. And then when two characters are conjugate under some Galois automorphism sigma, then also the orthogonal discriminants will be conjugate under the same Galois automorphism. Then you can, of course, restrict to subgroups. So you have a large group G. You want to know what's the orthogonal discriminant of this character chi. Then you can hope to find some subgroup H where this character restricts to, and just hope that there you know the orthogonal discriminant of this character there, and then you know it for the group above. I want to talk a bit more about the third and the fourth point at the end of this talk. And finally, what you can do is consider modular representations. So here, Brauer characters will get involved, which are just modular characters. And what you can do is basically you take your representation characteristic 0 and reduce it modulo sufficiently many primes, and then you get basically conditions on what your orthogonal discriminant could be. So there is quite a rich theory involved in the fifth point. But we now will, just for the last 10 minutes, I guess, take a deeper look into 3 and 4. So the first one just being permutation representations. So what I mean by a permutation representation is just the following situation. Suppose we have an orthogonal character of even dimension. That's just what we need to have an orthogonal discriminant. And now I want that the trivial character plus chi is a character of a permutation representation X. So what do I mean by a permutation representation? Well, that just means that there's a QG module V, in fact a ZG module, with some basis E1 up to En, such that X of G just permutes the basis elements. So the matrices with respect to the bases are just permutation matrices, so they have exactly one entry 1 in each row and column. That's just what I mean by that. And now what you can just do in this situation is you basically just define a bilinear form B on the vector space, which is just a standard inner product. And clearly B is G invariant and non-degenerate. Well, if you remember my first example of a quadratic form, this is basically the same. Like this is just a standard inner product on some, in this case, n plus 1 dimensional vector space. And the G invariance just follows by, well, you can just think a bit about this. But another way of seeing it is that if you take a permutation matrix and transpose it from left, multiply it to the Gra matrix, this is the identity here. And from the right, you have the usual permutation matrix, and you get P transposed times P, if P is a permutation matrix, and that's just the identity again. So the Gra matrix again. So this is, in fact, invariant. So now we have an orthogonal representation with character 1 plus chi. Now we can decompose this into, well, two submodules. The left one we will call W, and the right one is just, well, just the sum of all elements. And clearly, G also acts on this one. It acts in a trivial way because you take the sum of all basis elements, and because the group permutes these, you get a trivial action here. And the other one is this, is the space generated by E I minus EI plus 1. And we have also seen that in the second example. That's just exactly a second example. In fact, this quadratic space W and the restriction of Q respect to W is just this quadratic space AN of Q, which we've seen in the first example, and we know it's determinant. It's n plus 1. We have seen that. So we can conclude that the discriminant is the square class of n plus 1 up to a sign. So this is basically the proof of the following proposition. If you have an orthogonal character of even degrees, such that 1 plus chi is a character of a permutation representation, you can just write down its orthogonal discriminant. Okay, so that's all very nice, but do these actually occur, such permutation representations? Well, the truth is not all that often. There are some infinite families where you always have such a character. For example, alternating groups. Like each alternating group has an irreducible, let's say we take the AN, that always has an n-1 dimensional irreducible character, which comes from the restriction of the usual permutation representation of the Sn on n points, just the usual permutation representations. That one restricts to AN. And then you can always divide out this subspace, just the sum of all basis vectors, and this will always, the remainder will always be irreducible. And there you can always apply this proposition. And there are also some sporadic groups where this works. So the last thing I want to talk about is the adjoint involution, and I think that's a very beautiful way to compute orthogonal discriminants. And the setup is the following. So suppose we start with an orthogonal character chi of even degree n, and I want to denote k for the character field because I'm too lazy to just always write q of chi. And now we suppose that there's a kg modulo v with character chi, and now we take q to be some non-degenerate g-invariant bilinear form on v and just write b for bq. So this is just basically the setup for the definition. We have an orthogonal character of even dimension. We had, if you remember, we had this space q of x of this non-degenerate invariant forms. And now we just take any of these, which is q, and denote its induced form by bq. So that's just the basic setup. And what you have in general for any bilinear form that's non-degenerate, you have this so-called adjoint involution on the n-morphism ring of v. And this adjoint involution iota basically just tells you, OK, I have an n-morphism alpha, and I want to apply it to the first component. What happens if I don't want to apply it to the first component, but to the second one? And this is what this adjoint involution does. And if you have a non-degenerate form, this is unique. It's independent of the scaling of b. Yeah. And actually, you know how the adjoint involution behaves on isometries of the vector space, by which I just mean automorphisms that satisfy this property here. So they leave the bilinear form invariant. So you know if you have such an isometry, then you just know that iota b of alpha is alpha inverse. Yeah, just take one of the components and apply the inverse of alpha, and then you basically have the definition up here. And now, because we took a g-invariant bilinear form, the group G also acts like isometries on the space with respect to this bilinear form. So group elements will be inverted by the involution. Of course, you can do this also for matrices in the language of matrices. If you let B denote the Gram matrix, then you get this formula, and you get an involution of k to the n by n. OK, we can do that. OK, so but what's the point? Where do I want to go to? Now, what we can do is we consider this the eigenspace of this adjoint involution, well, written in matrices. And, well, we just consider the -1 eigenspace of this adjoint involution in the language of matrices. This is just a set. So, and why do we do that? Well, in fact, it's a very beautiful reason, because like that's the eigenspace for the that's again the eigenspace for the eigenvalue -1. And there's another way to write this down, namely the following. We can write this in this way. So that's just another way of writing this. And it's just a straightforward computation that this works. You just, yeah, we just use a definition, the fact that B is symmetric, and just compute it. So this, in fact, holds. It's just very easy to see. And now we just use a bit of linear algebra. So in addition to having a skew-symmetric matrix, if the matrix X is invertible, then X is basically comes from an alternating bilinear form. And by linear algebra, we know that these can be brought into this canonical form. So you always have these blocks of 0, 1, -1, 0 matrices. And you can bring it into this form. And now you can compute the determinant on the right-hand side. And that's just very easy to see that this is 1. So we know that the determinant of X is a square. So what's my point? We want to compute the determinant of B, because B is a Gram matrix of the bilinear form which corresponded to our quadratic form, and the discriminant of the quadratic form is an orthogonal discriminant because we're working over the character field. So we want the determinant of B, and so what we can do is we just compute the determinant of B times X, and because the determinant of X is a square, we can just ignore it. and we're left with the determinant of B. So the point is, we can just compute, we just need to find any invertible element in the set E minus B. Let's say we call it Y, and then the discriminant is up to a sign just the determinant of Y. Just because of the fact that the elements here look like this, and if we find an invertible element here, if you compute its determinant, well, you're left with the determinant of B, because the determinant of X is a square. Very simple. So if you want to compute the determinant of a symmetric matrix, you compute the determinant of a skew-symmetric matrix. And the advantage is that you don't have to know you don't even have to know the linear form for this. You don't even have to know B for this. The reason is the following. You can, that's just another straightforward computation. If we have now a matrix representation X with character chi, then, well, we know what the joint involution does to group elements. It just inverts them. And you can, in fact, show that E minus B can be written like that. And my point is, on the right-hand side, there is no B anymore. So if you want to compute the determinant of B, you basically only need to know your matrix representation. You don't need to construct your form. And this here can be very easily done by some computer algebra systems, up to a degree like 1,500 if you use Magma. But that's just way easier than constructible linear form that you might know nothing about. And in fact, you can even simplify this just by not taking the K span, but the Q span. Remember, K was a character field, so you just search for invertible elements here, and the proposition is the following. The discriminant of chi is just the determinant of Y for any invertible element Y in this set. And as long as you can construct a matrix representation or have one available, you can just, by a random search, try to find some invertible element here and compute its determinant, and you are done. So as a final example, how we can use this, we want to again discuss the group A5. And it has an irreducible orthogonal character, chi, of degree 4. In fact, this is this permutation. That's the character 1 plus chi, which is a permutation character, which I talked earlier about. So we expect its orthogonal discriminant to be 5 up to a sign, n plus 1, n is 4. And we now want to compute it in another way. And for that, we take a matrix representation X with this character, which you can actually construct from the permutation representation. And now the idea is, if you take any group element G of order 5 in the alternating group on 5 elements, its characteristic, the characteristic polynomial of X of G must be given by the 5th cyclotomic polynomial. The reason simply being, it has order 5, and we are working over, we have a rational matrix, so its characteristic polynomial must lie over the rational field and has to divide x to the 5 minus 1, because the order of this element is 5. And over the rationals, x to the 5 minus 1 decomposes as this one times x minus 1. And now you can, for example, use the fact that the group A5 is simple, so every representation is faithful, in fact, and in fact, nothing but the identity is mapped to the identity matrix. So you know that x minus 1 is not the x minus 1 to the 4 is not the characteristic polynomial. So now you can take any root of this. That's just a 5th root of unity. And then, well, we want to compute the determinant of this one. This is just a product of the eigenvalues of x minus g minus x minus g minus 1. And the eigenvalues of these are just the root of the 5th cyclotomic polynomial. So it's just the product of some roots of unity. And if you do the calculation, this turns out to be 5, what we expected from permutation representation. And in fact, this argument works in general for a group G as long as you find an element G that doesn't have eigenvalues plus or minus 1, because then this one will always be invertible. Just imagine you're working over the complex numbers, you diagonalize these matrices, and then the difference of these matrices can only have a 0 on the diagonal if the 1 meets a minus 1. So if there are eigenvalues plus or minus 1. Also, that's what I said earlier, if you are just able to construct a matrix representation, you can use the whole idea which I told you about with the joint involution to use an algorithm to compute the discriminant. That's actually something that I did for my master's thesis, and it works quite well up to dimension like 1,500. Yeah, and here, just again, what I said on the slide before, you can just get the orthogonal discriminant by considering a group element without eigenvalues plus minus 1. That's what I said. And here's the formula for the orthogonal discriminant. And, well, another corollary to this is if we have some group G such that G squared is minus the identity matrix, then, well, then G definitely has no eigenvalues plus or minus 1. It only has eigenvalues plus and minus I, so fourth root of unity. So you can apply this one. And, well, then you get that the discriminant is exactly this. And now, what's the determinant of this matrix x of G minus 1? Well, we know the character is real valued, so the eigenvalues I and minus I occur equally often. And it's real valued because what I said on the blackboard, an orthogonal character always lies in a rational field, its values. Yeah, and so we know the eigenvalues I and minus I occur equally often, and the product of I and minus I with equally often, which occur equally often, is just 1. So this just disappears. Yeah, and with that, I'm on my final slide. This is just the method that I talked about, and I would just want to say, even though that all looked very nice, there are still many orthogonal characters for which you can't use any of these, simply because the degrees get too large. If you consider finite simple groups of order 10 to the 9, 10 to the 11, or even higher, then the character degrees grow beyond 2,000, 3,000, 5,000, and you can't really expect any computer algebra system to construct matrix representations, so this trick with the joint involution simply won't work anymore. And, well, the best shot we have is some modular representations because they're easier to construct, even to high degrees, and then infer some constraints on the orthogonal discriminant on characteristic 0. I just want to say that even though this all looks very nice and beautiful, there's still a lot to do. Yeah, and with that, I'm at the end of my talk. I want to thank you for your attention.